the electrochemical synthesis charge transfer salts. And so in abstract, organic charge transfer salts, they're known to exhibit, like Dr. Cole said, a very wide range of electronic properties. And we wanted to see if we could change these electronic chemical doping. And we found that this is actually feasible. So we went on with the experiment, seeing what we could get from it. So electrochemical synthesis, what is that? So you need an electrochemical cell like this. I don't know if you can see that. Or as we did like this. And between here there are two electrodes. One is a cathode and one is an anode. And you apply voltage between them and things flow through this slit. And so charge transfer salts, there's a lot of stuff done on them. They can be insulators, conductors, semiconductors, superconductors, and they all have really interesting electronic interactions at low temperatures. So our system, which is a superconductor and spin glass, was formed from this solution. This is copper thiocyanate, and when you put it in solution, it splits up into a copper anion, or cation, and a thiocyanate anion. And then the other molecule we used is ET, which is, you'll see later, it's a big molecule. When it's put in solution, it actually bonds with itself and forms ET2, which has a positive charge. And so when these two come together, they actually make ET2Cu thiocyanate 2. It's a long name. All right, so the process. We had a bunch of reagents. One of them, as I said, was ET, the BEDT-TTF, better known as ET. So this is the donor molecule, and it's the molecule that actually donates the charge for charge transfer salts, as is in the name, charge transfer. And like I said, it pairs up with itself and gets that charge. The copper thiocyanate is what adds the copper group and the thiocyanate group. And the potassium thiocyanate is actually what helps facilitate breaking this up so that it can bond with another thiocyanate. And after that happens, a lot of potassium is left behind. And 18-crown-6 is just a facilitator molecule that helps make the acceptor molecule, which accepts the charge from the donor molecule. And then we used trichloroethylene as a solvent, TCE, and then 5% ethanol, which helped the reagents get into solution faster, because we wanted to do it as fast as possible. So there's a lot of steps to doing it. So we first had to clean the glassware. We did this with methanol, DI water, and aqua regia. That's just to make sure we didn't have any kind of things that could mess up the reactions. And then the electrodes were cleaned with sulfuric acid and applied voltage. So we put them in sulfuric acid and we applied voltage, and that created more nucleation sites, which hopefully would help us grow crystals better, because the more nucleation sites you have, the better growth rate you'll have. So recrystallization, we had to recrystallize critical reagents, which in this case were 18-crown-6 and potassium thiocyanate. And so 18-crown-6 was recrystallized in acetonitrile, and the latter one was recrystallized in ethanol. Then we had to prime the H cell. To do this, we took a little pump on the H cell, and we cycled the TCE through it. We just pumped one side, came through, other side came through. And that helped us remove, and that just helped us so that the slit was clean, basically. But before we did this, we cleaned the TCE by pumping out all the water, because water is very bad for a reaction. It'll break down the crystals. We don't want that. And so then we added the reagents. On the anode side, which is the negative side of the electrode, we added 18-crown-6, copper thiocyanate, potassium thiocyanate, TCE, and ethanol. Now on the cathode side, we added ET, 18-crown-6, copper thiocyanate, potassium thiocyanate, and everything else, TCE and ethanol. And this is because on the cathode side is where the reaction actually takes place. So this is the biggest contributor to the molecule, so we wanted that to be on the cathode side. And after that, we applied 1 voltage potential to the electrodes, and we let them grow in a dark area on the optical table. The optical table was so we can prevent most of the vibrations, because the crystals are very sensitive, and they're also very sensitive to ultraviolet light, hence the dark area. So this is what we got eventually after 2 weeks. They're very small, and they're actually pretty flat. And so here's a closer up view, and the picture's pretty bad, unfortunately, but I don't know if you can tell, but it's kind of feathery, and it's got a little bit of holes in it. And we determined that that was because the 1 volt potential created a 2 microamp current across the electrodes, and that was too fast for it. Ultimately, realistically, we'd want to redo it, but we didn't have enough time. So we just went on with the rest of our experiment, which was to grow the dopants, or which was the dopant. So we took what was left in the H cell and split it up against 3 smaller H cells. And after that, we added the dopants. For one of them, we added silver thiocyanate, 30 milligrams. Another one, we added sodium thiocyanate. And the last one, we added mercury thiocyanate. Now, copper has 29 protons, and sodium has 11 protons. This would have a higher reaction energy than this one, so it's more reactive. Same thing here. This one has more protons, silver, and this one has more protons, so these are much less reactive. And we applied 1 voltage potential to these as well, because this is the favorable voltage for forming our crystal. And then after 1 week, we got this. This is the silver thiocyanate, and this is the sodium thiocyanate. Now, this is a lot of copper that I don't actually know how it got in there, but this is really what's interesting. I don't. This is the sodium crystal. It looks pretty cool. Unfortunately, the mercury crystal was very hard to harvest because they were very small, but they were there. And so then I decided to look at them under the SEM. This is the control group, and this is the silver dope sample. Now, this one, I don't really know why either, but it started breaking down in the SEM. And I found that very interesting. I would like to study that further. The sodium dope sample was way too small to get on the stand, so unfortunately we couldn't see what that was measured, or what that looked like. So now we wanted to measure it to see what we did to it. So we want to measure it, it's at low temperatures. So in order to do that, we needed some kind of probe. That. And then here's the end of the probe. It's just got a little piece right there. And so, as I said, we wanted to go from room temperature to 77 Kelvin. So we used liquid nitrogen and put that in there. But if we put that in there just as this probe, that would have killed the samples. So we incorporated this probe and we vacuumed it out so that there was less energy transfer, or slower energy transfer to the crystals. And yeah, here's the results. So this looks beautiful. It actually matches this perfectly, although we didn't go all the way to the temperature they went to. And we didn't have a pressure at all. But this is good because it proves that we actually did grow the crystal. And then this is the sodium one. As you can see, the curve is actually beautiful. It has an insulator-like property, which means that we actually did change the crystal right around here when it starts increasing. And then this one looks crazy, but it actually is good too because we actually did change as well. Right around here, where the peak, right here. The peak for this one is about 100 Kelvin, and this one is about 150. So that's good. It means we actually changed it. And so in conclusion, we actually did show that it is possible to, through electrochemical doping, to change the electronic properties of this organic transfer solvent. And as Dr. Paul said, this is really exciting because it's the first account of this being done. And hopefully we can study more things like its superconductivity, density wave states, and its magnetic systems. Thank you.
Questions?
How did you remove the crystals from the H cell?
Kind of pull out the electrode and then just clean it off.
Were they on the electrode or were they
They
sitting
were on the electrode, yeah. The other ones kind of, they were a little bit, so we left them there. Oh, shoot.
So any of these samples show anything magnetic?
We didn't test the magnetic properties of them.
And
So,
do you have any idea why the silver doped sample looks so different compared to the sodium doped sample?
I do not, unfortunately. I would love to further test that.
Well, I'd like to make a comment. Collin was in my What Physicists Do class this past semester, which is our physics colloquium series, and the students have to prepare by researching the speaker and then writing up points that they've taken away or questions that they had from the talk. He's the only student that was able to stump me by coming up with questions that I in class, and I had to send his questions off to 2 of the speakers. Having him in his class, and this is really amazing work. So let's thank him again.
Yeah.
Yeah.
Okay, so our next speaker, Dr. Shi.